Hopefully last week was more pleasant for you than it was for me. Any questions? So we've gone over NumPy and pandas, right? So how to do, the tools we can use to do some data analysis. And later in the course, we'll move on to Spark, so we can scale this up. So that's sort of a big jump between, running it, on a little machine, and so there's an intermediate we can do. So the library called Dask, which does parallelize Python code. We're trying to parallelize things. There are several things you have to worry about. One is the size of your memory, right? And once your data gets larger than your memory can handle, of course, operating systems will then page it out for you. But they're not very smart in terms of what pages would you bring in when, right? It's like, well, you got a big block of memory and you want that one, so we'll bring it in. So it's maybe to try and have a smarter algorithm based upon what you're doing to break things up, right? And of course, the other one is, we've got multiple cores. Well, does anyone have a computer doesn't have multiple cores anymore? I mean, and you can actually buy machines with multiple processors, right? The problem we have with Python is the global interpreter lock. And the basic issue is this. Anytime you've got any sort of concurrency or threading, separate processes running, you have to worry about memory read-writes, right? So whenever you want to write to memory, you need to make sure that no other thread or process has access to the same memory and is reading and writing to it. So a language like Java, right, what they do is they do it at a fine grain, right? So I can have an object, and I can have a method synchronized on an object, and then whenever I call synchronize method on that object, right, then there's this process where we lock down that object to make sure no other thread is accessing any synchronized method on that object, which means threads elsewhere can still be running around no problem, right? When you use Java, what you don't realize is how hard that is to do, right? For one thing, for you to get a lock on that object, first you have to get a global lock to make sure that no one else gets the lock at the same time. And it took the Java team some time to get all this right. And there's actually methods dealing with concurrency that they said they were going to implement, and they were in the JDK, which were never implemented because they couldn't be implemented. It's really, really hard to do and get it right. And so a lot of systems don't go that way, right? They have their own threading system, often called green threads. You're actually only using one operating system thread, and then you're doing the time slicing internally. What Python does is you can run threads, but there is a single lock, right? So when a thread wants to run, it grabs the lock, and no other thread can do anything until the thread releases it. Which means it doesn't matter how many threads you run in Python, only one is running at a time.
This means you're going to know multi-threading. You have to write in a different language.
So the question is, that mean if you want to do multi-threading, you have to do it in C? That's part of the problem. All this Panda code is really written in C, and that C code is not thread safe. Right? And so if we're trying to run pandas, right, in a thread environment, how do we protect that memory given that you jump into C code and there's no protection at that level. So what this library does, Dask, is it says, look, we're going to build a scheduler, right? And then the scheduler is going to, depending on what level we're looking at, it'll take your big, data frame, break it into smaller data frames, right? And then allocate different data frames, different threads. And so now we know we're safe, right? Because we know that we schedule them. Now, there are some ways to actually get around this global interpreter lock, but you have to sort of, I don't know how to do it because I've never done it, but you have to basically guarantee that this memory is not being used by anyone else, right?
Yeah. Actually, I once tried to use the Python to write a kind of multi function that could play two kind of like and the computer can play the sound simultaneously. So if they're kind of like theory, the sound can run can only run one because I can indeed kind of hear two because there is a library for the multi.
In general, no, there isn't, right? And this is a well-known problem with Python, is that
but that is exactly something because I just tried to pour the play MP3 of the two pages.
And how are we playing the MP3s?
I think there is a kind of like.
And the library does what? It's probably calling an OS call, right? To play that, and so you're making two calls operating system, and so parallelism isn't happening at the Python level; it's happening at the operating system level, which is fine. Right? Right. So we have this, and the problem is all this Panda code is written in C, and it's not thread safe. And no one has come up with a good solution to this, and it's a well-known problem, and it's probably not going to get solved. So this Dask library, it will run Python code in parallel, and there's a high level and low level. High level, you basically create a dash data frame, and the dash data frame basically is implemented by having sub data frames for Panda, and then you can schedule those, right? And the low level, we can specify, this piece of the code and have it delayed, and we'll see an example of that. And you can run it on clusters, so you can have a particular cluster machine, so you distribute it, or if you've got a single machine with multiple cores, then you can use the cores. There's a bunch of different schedulers. And so the local thread scheduler, it uses regular threads. It still can only run Python to one thread, but they've arranged it so that we can schedule the C code underlying pandas to run in parallel. And the nice thing about this is you don't have the inter-process communication to worry about. Right? It's all basically in the same namespace, right? Memory space. There's also a single thread, and that's their primary for debugging. So you can if you ever deal with concurrency issues, at some point you realize that you get settle bugs. I've known of projects where they're doing all this parallel work, right? And they have a bug and they can't find it, so they start putting print statements to figure out what's going on. The problem goes away. You take them out, comes back again. So at least one project, the solution was see the print statements in, and it never happens, right? And then there's a scheduler for actually distributing on many machines. And of course, you have to set that up, and you have to have a client and all the machines to get the well, it's on a local machine and then a cluster. That also, Dask delayed basically creates a proxy object for a piece of code that you can run later. So here is a several fake functions that pretend to taking time. Most examples come from the Dask tutorial. And then when you look at how long does it take to run these, do 2 increments, well, of course it's going to take 3 seconds, because each one takes a second, right? Now we can import Dask for delayed, and now it's the key thing here is the syntax is delay the function you want to call and then the argument list. Basically puts a wrapper around it, and then when you do it this one, then it takes basically no time, but it's not doing anything. We won't do anything until we actually call compute on it. And it takes 2 seconds because you can parallelize the 2 increments, but you can't. Yeah, it has to wait until they're both done, right? And you can actually visualize the scheduling. Visualize, right? So I give a nice little graph to show you. So far, so good. It's slightly more complicated, right? So you have list the numbers, and you call increment on all of them, right? And then append the results. And then you want to sum the results, get the total. Several things happening here is as soon as this is without using delay to delay. Once I call delay an increment, and I call other functions on it, those are also delayed, right? So we get still just taking like 1 second to compute this. Why? Because all those increments can be done in parallel. And when you visualize it, right, again, we get all those increments are done in parallel, and then the sum is. So it shows you that, yeah, it's doing it in parallel, right? Yeah, keep in mind it's not delayed of the function, right? Because this will evaluate the function first. It's delayed function name and then the argument list. Each time you call compute, you want to be doing lots of small little things, right? So it can actually break them down into smaller pieces, do those in parallel. You want small pieces, but you also want to be doing something computational, right? I mean, adding numbers is like the overhead of calling delay is going to, in the previous examples, just completely dominate this. So an example they used is the data set where you have all the flights leaving the 3 airports in New York City, and there's 10 files, and each file is about 25 megabytes, so it's about 250 megabytes total. There's a bunch of columns. The ones important are the origin, which airport it's taking off from, and the departure delay, how many minutes the plane was late in taking off, right? Because there are other ones where it's going, arrival, so there's 10 different files. So here is, right, an example, computing the mean delay time for each airport. Sort of doing it the hard way. So this is just a list of the file names, right? So they're all files in a directory, right? And so this was a path to that directory, directory name, and so we cycle over all the files, read each one, do group by origin, and then compute the sum, compute the count, right? And then we can do this, compute the sums, do all the counts, and then we can divide and get doing straightforward Panda to get takes like 5 seconds. Calling delay on it, and then doing all this computation again. All these are delayed because we're and we call compute. We're now going to compute the sums and counts. Now we're going to do, and again the time goes down to 1 point. Shows several things. One is, right, using delay, we are getting parallelism. Shows how when we get delayed, right, we're doing other operations on the delay, but those are also delayed. And generally, you probably wouldn't want to go to all this work to compute that. There are simpler ways to do it, right? And so this delay is just a wrapper, right, or a proxy. And so I'm doing a read, right? I'm not actually reading that file. I can now use standard data frame operations on it, and those are delayed until we call compute. Higher level, go ahead.
With delay, would it handle if, let's say, two functions both for writing the same file? Let's say you delay functions. Would it automatically handle the synchronization for that file, or is that kind of shame on you?
Yeah, you don't want to do that.
So you said you just want.
Higher level, they have what's called arrays, right? Which is basically NumPy arrays that you read an array and you'll divide it into smaller blocks. Those are NumPy arrays, and then those will be scheduled. Most examples aren't very exciting because you just, okay, so what's happening here is, I'm reading this special file format, getting the data frame out of it, and now I'm getting that data set and converting it to a dashed array, and saying how large I want those chunks to be. Now again, when I call operations on it, those are being delayed until I call compute, and it's going to then, in this case, create the sum. You can just compute the sum of each block and then get those results and sum those together. And you can do most of the operations that you can on Panda arrays or NumPy arrays. And the Dask data frames, again, the same thing. You read a data set of the Dask data frame. It's going to break into smaller pieces. Those pieces are going to be Panda data frames. And then when you do operations on them, right, they're not done until you call compute. And then to try to schedule them to be done in parallel. So if you get a large data set that won't fit in memory, that's going to be more efficient because you can break it into smaller pieces, and they can read. And the Dask will read in one piece at a time, right? So you can perform operations on. And if you want to have long computations, you can do it in different cores, right? Or if you want to put it, again, distributing a cluster. So again, going back to the New York City flight data, there is a read CVS, and the nice thing is that again we can give it a directory of files and read all the files into one data frame, so we don't have to read them one at a time and glue them together. But the problem is when you do this, it's not reading the entire file. It's like, okay, it's scanning the first part of the file to figure out what the rows, columns are, and the data types are. And the problem with trying to guess your data type is that it's not always going to be correct. And it got some of them wrong. The date time, it thinks it's an integer. Like, no, it's not an integer. It's it's a date object, right? So you can actually specify, given a column, you can specify what the So then we can compute what's the maximum delay? Well, again, it's giving it depth delay column, and compute the max, and then do it when you compute. Once again, it's breaking smaller data frames, right? Computing the max each one, and grabbing the result. And and again, when you call it visualize on it, shows you you broke into pieces. Yeah, it's really hard to read even. Something more interesting is how do we actually compute the mean delay, per origin. Well, so we can just grab the origin and the departure columns, right? Call group by an origin, and on that compute the mean, and then call compute, and now the one problem is, like I said, it's only like 250 megabytes file, right? Again, we can see how it's even harder to read, but it shows you that it is parallelizing it. Right, so there's a parallel version. So we can first call compute on the data frame itself to get a panda data frame, a single data frame, and then do the same set of operations on it. And it took 679 milliseconds as opposed to 2.12 seconds. Yeah, given the data sizes, this is not worth it, right? When's it worth it? Well, when the data doesn't fit in memory. But 250 megabytes, 8 gigs of memory on this machine, right? There was plenty of memory. The other thing again, slightly interesting is look at the CPU time, almost 500 milliseconds here, 273 milliseconds, 29 milliseconds, 200 milliseconds. So why is it that using the Dask version, the CPU time is significantly less, even though the wall time is significantly more?
Because of the scheduler.
Well, you have to ask what is that measuring? Is it measuring the thread that the schedule's running in, or what the other threads? Right? If the scheduler is forking up other threads, when you measure the CPU time of the main thread, are you getting and then why is there here the total is 715 milliseconds, but the walk time is. So how can we use 715 milliseconds and only use 697 milliseconds of wall time? Wait, no. The total CPU time is 700 milliseconds, and the walk time is less. So how can a single thread use 715 milliseconds to only take 679 milliseconds wall time? Oh, but it's taken this long to do the computation, right? So the time from my start to computation to end the computation is less.
Somehow. Time where it's actually done. For some reason, CPU schedule. Longer.
Is anyone taking an operating systems course? How do you measure the user time, system time? How's that done? Particularly since there's multiple threads, other threads running, right?
Yeah.
So each thread is getting time sliced in and out, right? How do you keep track of how much time is used? Yeah, but how do you keep track of how much time was used?
I mean, I guess like. Clock.
So we're doing that for every thread, every time it gets swapped in and out?
Are you saying that the others, they're, ran out of RAM, then come back to the RAM? Or are you saying that the computer?
Yeah, I mean, it's been a long time that we've had a commercially available standalone computer that wasn't doing threads, right? And you know, either you're doing a Unix-based machine or a Windows-based machine, right? And both those machines, and look at the task manager, right? There's a lot of threads running around. So it's how important is it for the operation of the machine that we compute these results accurately?
Is that kind of like different program they run? We are going to fetch for the running data information, so that is time that not just the one.
Could be, but usually what happens is when you're measuring the CPU time, you do it by sampling. And it's not very accurate. Right? On multi-unix machines, you're probably plus or minus 25%. Right? The most important thing is that it runs correctly, right? And if you're running 200 milliseconds, who cares, right? If it takes 25 minutes, so you have to be careful with numbers, right? Because it can be a large percentage error, yeah. So again, right, so Dask, we can run things in parallel, and it can be useful, but you have to be careful in the sense of if it all fits in memory, just use pandas, right? It's going to be faster. And so it was like the panda version was like 3 times faster. And just for fun, I ran the same thing in Julia to see how it compared. But I had to then read one file at a time and glue them together, right? Once they get glued together, then you have, pandas it'll ignore missing data, so you can just sort of forget about it. Not Juliet, no. When you try and compute something, it's like, I'm sorry, but there's missing value, so. And so it took 0.24 seconds, 0.25 seconds. The one has to be careful, right? Each language has different performance characteristics. So the I/O in Julia is much slower. So it took a long time to read the files in. And usually the first time you run Julia code, it compiles it first. And so the first time you run it, you get the time it takes to compile. And if you're running something that takes 0.24 seconds, then the first time you run it, it's just all compile time, which is a lot slower. And this exclamation point is important because if you say drop missing, it creates a new data frame with the new data without the particular missing points. And when you do that, time goes way up because you have to allocate the memory for that new data frame. And that would then dominate. And then there's they call it JulieDB, which is not a data frame, but they claim it's in memory database. And it will load everything for you, which is nice. And you can then do interesting things in it took even less time. But again, reading the data took really a long time compared to Python. Right, so Dask is just a tool we can use when our data becomes too big, right? And the nice thing is that it pretty much follows mainly the pandas data frame, so we can use almost all the same panda methods. So we don't have to jump all the way to Spark and learn a new system. Questions? So this will be, for some people it will be too fast, and some people will be complete review. Yeah, so some basic statistics, right? Mean is just what we normally call average, right? Median is that middle value, right? The mode is the most common one, common value. Variance is a measure of how, right? Standard deviation is also a measure how spread it out is, because it's normalized, right? Quartiles, right? Of course, when we talk about means, there are different types of means, right? We normally mean just arithmetic mean, but there are geometric means, there are different types of means. Yeah, so variance is just like the spread. You take.
Variance is just the maximum minus minimum?
No.
Is it compared to the mean?
Yeah, yes. Right. You basically take the difference in mean and all the values, and you square it, and you sum that up and divide by n. Yeah. This is where life gets really subtle. When you say, "Well, I'm going to compute the mean," right? Well, you normally don't have all the data, right? You have a sample of data, right? If I compute the mean height of students, and I take the mean height, compute the mean of height of everyone in the room, that's not all the San Diego State students, right? And that introduces errors. This is not, it's not the actual mean, right? And that will introduce a bias, because if you don't sample correctly, it's not going to be right. And so there's this crazy formula where instead of dividing by the number of items, you divide by the number of items minus 1, and that supposedly helps correct this bias in the sampling. But again, we're making certain assumptions about the underlying distribution, right? And we're sort of used to these bell curves, right? You flip coins, heads and tails, and the other distributions, right, which are skewed different ways. And so when you start computing, when you got a sample from those populations, computing the mean that way will not give you the right result. And so we can, that's why statisticians are so important, because they know all the ways of correcting all this stuff. Right? And so, the Python will compute all these for us, right? And right, compute the mean. It uses the Bessel correction. And you can also get a measure of how skewed it is. Right? It's like, right? I mean, so I guess I'm worth $20 billion. Right? So you have to be careful with mean, right? Just a mean is not, doesn't tell you everything, because in the first case, the variance is huge, right? In the second case, both of them are very wealthy people, and so right, there's a huge variance, right? So these are just ways to help describe what's going on, right? In some ways, not. And the problem is once you have huge data sets, you can't look at the individual numbers and make sense of it, right? We have to infer things by doing computations. Quantiles, right? It just divides the data into queues, equal amounts of data, right? The quartile or the fourth quantile is the most common, right? Divide the data into 4 equal amounts. So we only need 3 places. And in Python, we can compute it, right? So it's just quantile and give it where we want the break, percentage-wise. Right, so it tells you. And so commonly, when you see charts like this, right, they show you the median and then the 2 quartiles on either side. Right? And usually they do that because if you show the whole data set, there's usually outliers, which make it look. Because you might have, some CEO that still considers himself to be a programmer, right? And then he might be using $100 million, right? And then you've got some high school student who's working for $5 an hour, right? And they, right, that's like. There's a data set as part of our data set. Just someone did a survey of academic salaries based upon the rank. There's 3 ranks. Actually, there's more than 3 ranks, but lecturers are like subhuman, and then they divided the disciplines into either theoretical or applied. how long is their PhD, how long they're working, male, female, and then their salary, right? So here's plotting the salary versus the sex, right? It's hard to tell much, right? Although this range, we don't see any females, but otherwise we can't tell distribution, right? The rank, we start to feel more right, there's more yellow down here, and then right, and then finally full professors. Slightly more informative graph, right? Is like, okay, years since PhD, salary, and then we can plot all the points, and then look at the different ranks, right? Right, the professors, they don't go much beyond 10 years. Why? Because usually they give you 6 years, and either you like get promoted or you get fired. Right. You also notice that the slope is negative.
That's the gender. That's
Yeah, it's a classical salary inversion in that as time goes on, right, the competition with higher faculty it increases, and so you tend up giving new hires a bigger salary. That also happens in industry, right? It's like, and the same thing happens. Right, the next group is negative. For associate professors, there's not. I mean, once you're tenure, you get associate, and then you can stay associate for the rest of your life. It goes negative, and then finally professors, full professors, will get. Now, at least at San Diego State, the salary inversion got so bad. There's now a ruling that you can't, when you hire a new person, and you can't give them a higher salary than the lowest paid person in the department. Which is really a problem when you're hiring, because you're like, what do you mean? That's all they can pay me, right? So, you can see how much information we can learn about this, right? You know, it points out, you really want to be an assistant professor? Like, box plots, right? Right, so you get the median, right, and the 2 quartiles above, and then you get, it's called a fence. And it's, you know, frequently as well, this, right, the first minus the third, right, basically the, right, the times 1.5, and then we give it a range, not the entire, and then if there's outliers, not going to show the outliers to show that there are things beyond that range. So doing a box plot, right, is on that data set, looking at applied versus theoretical. The median is slightly less, but when you start looking at, it's a bigger range for the applied people. This really, right, like, that barely reaches the median of the associate professors, right? Another plot where we're plotting, right, each group, how many people are at each salary rank based on sex, right? So now we get well, given that there are fewer associate professors, there seems to be a higher percentage of females, right? Another plot is looking at just the outline, not the actual dots themselves. Gives you a view again. The bulge is like at the low end. Here the bulge is at the higher end.
In this plot, does the width of the plot, does it represent the median or the interquartile range?
I'm not sure. I don't think so. I guess it's a measure of how many are in that. We're still doing it by salary, right?
Yeah.
So it's a measure of how many people are at that salary.
I'm just wondering, why is the plot more wide at certain locations than at the other?
Oh, because there's more people are at that.
Oh, more people? Okay.
More people, yeah. Right, so again, statistics can help us just understand a little bit of our data, and plotting can be very useful to help us understand what's going on. So I came across this story. Apparently, it's a famous story. So it's probably not true at all, but it's such a good story, no one cares. The basic story is Poincaré was this mathematician, right? A French mathematician, and bread is really important to the French, right? I mean, it's like a big deal. And this was back in the 1800s, and so the bread was highly regulated. You just couldn't. These days, of course, you got these machines, you just spit it out, and when you go to the store and you buy a pound of bread, you know it's a pound, right? Because this is back when bread was handmade and loaves, right? So the story is Poincaré, of course, every day you buy your bread daily, you just go to the local store, buy it, bring it home. He suspected that the baker was cheating, right? Because each loaf was supposed to be a certain weight, but of course it's handmade, so it's not exactly that weight, and so some are going to be higher and some are going to be lower. And so he's a mathematician, so I go, okay, how do I prove that this baker is cheating? So you can go to the authorities and say this guy is cheating, right? Prove it to him. So he did it, right? And of course the baker was fine, but he could still bake, right? And so of course he's a local baker, so Poincaré still goes there and get his bread, and the baker's like, okay, you ratted me out, so I'm gonna make sure that you're not gonna rat me out this time. So he always made sure he always give the guy, Poincaré, one of the larger loaves, right, heavier loaves. And so the story goes, Poincaré then said, "Oh, he's cheating us again still." And he was able to show that, he was selectively giving Poincaré the heavier breads, right? And so the idea is like making distributions, right? And then we'll look at another example. But the Poincaré, right? So we all know the standard normal curve or bell curve, Gaussian curve, right? And it's given by a Pantone formula, which you're all, I'm sure, as well. And there are two parameters. One is basically the central point, and then the standard deviation. And once you do that, they're specified, right? And of course, we can again, by specifying where the meaning is and the standard deviation, we get higher or lower curves. And then, again, since it's a standard curve, we can compute, once you go so far off the median, how much of data should fall in that range, right? So now we get the same issue as computing the distribution of a population and a population of a sample, right? And the smaller the sample, right, the less clearly less accurate it's going to be, right? So if we wanted to know the distribution of heights among students in San Diego State, well, we take a sample in this room, we're going to be off somewhat because there's 30,000 students. If we measured all 30,000, then we're going to have the measurement of the entire population. And so if we did all computer science students with a bigger sample, but that would be biased because we're selecting a particular group, right? Computer science students might be taller or average or smaller than average, right? I do this random sample. But then if we have a random sample of population, right, the error is basically the standard deviation by the square root of n, of course, standard deviation of the population, which we don't know, right? But it is divided by, right, the square root of n, so the larger n gets, right, the smaller the error goes. But the problem is the square root, right? And so if we want to reduce our error by a factor of 2, we need to increase our sample size by a factor of 4. So hypothesis testing, if you're a statistician, this is all old news, right? So why the hypothesis? The hypothesis is that the baker is cheating, right? That is our alternate hypothesis. The status quo is the baker is not cheating, right? Right. So not cheating. right? Alternative hypothesis is that we suspect that the baker is shaving off a little bit of the loaves, right? In terms of the website example, right? It's a common thing to know how long people spend on your web page, right? And people, these big companies are always doing tests, right? They're modifying the pages and measuring how effective it is in terms of how long you stay there and how many more things you buy or whatever, right? Right, so. And so then we measure well, unless we've got a camera, looking at the baker 24 hours a day, right? And secretly somehow measure each loaf, right? We don't know for sure, right? So we're just going to probabilistically think, oh, okay, the probability that the distribution we've measured is not what it should be is small enough, right? So the standard measurements are p equals 0.5, which doesn't seem all that great when you consider that means like 5% of the time you're wrong. And then 1% of the time, or and so the first part of Pointier's story is that you buy in loaves of bread over time and you measure each one and look at the distribution, compute the mean, and what's the probability that a sample of that size, right, the mean will be not where it's supposed to be, right? And let's see, yes, types of errors. False positive is when you accept H1 when it's not true. False negative is you reject H1 when it is true. And apparently that's also one of the problems they have with the current test for the coronavirus is you get a lot of false negatives. And so people have to get to measure them 2 or 3 times, and it takes time. All right. So statistics doesn't prove, right, that one thing is caused by another. Right? It just says, look, the probability that H1 was correct is this much. Yeah, so there's this very disturbing trend in medical science and psychology studies. So there's a Center for Open Science, and they looked at 100 published psychology studies to try and reproduce them. And 97 were significant to 0.05. Only 36 reproduced studies had significant results with p less than 0.05. And these were published in top journals, not No, so the 47, right, the results were within 95% confidence interval of the so this researcher has spent most of his time explaining why a lot of the results are just wrong. And it is leading to some problems because some scientists are saying that they can't even reproduce their own results, right? They reproduce their experiment and they can't reproduce it. Another paper is like, okay, this. And it's just things are not reproducible. More terminology. Sensitivity is basically how good are you at predicting, finding each one correctly, right? And specificity is how good are you at, finding all the the confidence interval, right? This interval which will contain a certain percentage of it, right? So the standard distribution, the confidence, 1.5 times the standard deviation should give us 95% of results. Right. So the first part of the Poincaré study is, right, he just went to, sampled a bunch, bought a bunch of little spreads, recorded the weights, and then computed the mean, and then computed the probability that a mean, if you get that mean from the sample, from the distribution of what it's supposed to be. So look at that next time.
I got a question. So I'm doing some research in climate data, and I'm using Python and using Jupyter notebooks. And I was wondering if you knew anything about a log scale and how the matplot library log scale.
Yeah.
Do you know how it interprets negative values? No. I can't find any documentation on how it handles negative values. Or maybe if you have a resource that you can point me to.
But now, what happens when you do have negative values?